Hello, Royals. For lesson 1.8 on transforming quadratics, if you're looking for lessons online, make sure you're looking for the COVID version. This lesson has been placed here specifically to help students that won't be getting the full experience of a regular classroom and maybe found grade 10 to be a little bit rushed as well. So 1.8 COVID version, transforming quadratics. I just want to do a couple of sketches and review all of the language that we used in the lesson. So both of these are going to be transformations of a parent quadratic function, which I could call h of x equals x squared. I'm going to use more function notation than is done in the printed notes as well. So your parent, h of x, the h machine squares your input. So you input 0, h of 0 is 0 squared, h of 1 is 1 squared, h of 2 is 2 squared, h of 1/2 is 1/2 squared, h of negative 1/2 is negative 1/2 squared, h of negative 1 is 1 squared. The h machine squares inputs. And you get a curve that has a axis of symmetry of x equals 0, an optimal value of 0. It's a minimum value of 0, a vertex at 0, 0. And it's symmetric about the y-axis, I suppose. You could talk about its step pattern as well, over 1 up 1, over 2 up 4 kind of thing. Good. F of x and g of x are transformations. You may have become comfortable with vertex form in grade 10. We won't really have vertex form for other functions, but we will have transformational form. So just transition to there. The function f has what I call a vertical stretch by 1/8. Please use the word stretch and just call it a fractional stretch there. It's probably simpler than saying compression. If you're going to use a different word, just make sure it's clear that you're going towards the x-axis. Translated left 6 and down 1. Again, the translation left 6, let's just look at this curve right here. There. In fact, let's change that example. The easiest way to remind yourself to understand why this has gone left 6 is asking, what is the root of this expression here? What value of x would make this factor 0? Well, if you want x plus 6 to equal 0, notice how you would have to perform the inverse operation to isolate x, and that gives you a root of negative 6. Okay, you're not making your input 6 larger. You're saying if you're adding 6 before you square, your inputs can now be 6 less than that. I think the examples sometimes used in the lessons are you're trying to save up for $100. If someone is going to give you $6, you don't need $6 more. You need $6 less to meet your goal. And then my point about the vertical stretch, I don't want to see a curve that is ridiculously flat here. You will probably be arguing that you have stretched your scale instead of stretching your curve. And with no other references on this graph, the only other point of interest that might be labeled would be the y-intercept. Although notice the question didn't tell us to label intercepts. For this curve, for example, I don't think I will be finding its intercepts. If I wanted to find the y-intercept, let me just try selling you on function notation again. The definition of a y-intercept is the value of y when x is equal to 0. It's a distance and direction from the origin to where your curve crosses the y-axis. It is not where your curve crosses the y-axis, and it's not a point. This is useful for us because now in function notation, you can redefine your y-intercept as, in the general case, f of 0. Our f of 0 value here is going to be whatever 1/8 of 0 plus 6 squared is. Please do not expand this to get it into standard form to try to read off what the y-intercept is. Sometimes students that have grown up with reference sheets will have on a reference sheet that in standard form, the y-intercept is c, and that's true. But that doesn't mean that that's the only way to find the y-intercept or even a good way to find the y-intercept. I expect students to understand the definition that the y-intercept is the value of y when x equals 0, and that means you can calculate the y-intercept from any format at all. So yeah, I substitute in x equals 0. 0 plus 6 is 6. 6 squared is 36. 1/8 of 36 would be 18/4 or 9/2. So this height right here is 9/2 because I say so. I just labeled it 9/2. You might argue and say, wait, isn't this like 5.5? Shouldn't it be up higher? That's only if your y-axis is going to be in the same units as your x-axis and the same scale. And I don't want that to be the case. Draw yourself a smooth curve, and wherever you cross your y-axis, label that your y-intercept, if you are asked to label your y-intercept. It's not a bad check to make sure you're opening in the correct direction here. But g of x is a parent quadratic that has been reflected across the x-axis. You could call that a vertical reflection. Translated right 3, if we cover this up, the root of this function would now be 3, right 3. But the vertical transformations are more straightforward. This adds 5. Here's me doing rough sketches. I feel like it's a bit of a mess, so let me tidy that up. I'll label a vertex at 3, 5. Now this is actually a little bit dangerous because sometimes students believe that you go right 3, up 5, and then you open down, when in reality the vertical reflection occurred first. This will cause problems for us with our orders of transformations. For example, if I were to reflect this curve vertically, if I were to reflect it across the x-axis, which I think would be a more appropriate term to use, it wouldn't look like this. It wouldn't be opening up from the vertex. It would be reflecting across the x-axis. That's not happening here. But, okay. If you feel the need to, you could calculate your y-intercept here by calculating g of 0. G of 0 would be the opposite of 0 minus 3 squared plus 5. 0 minus 3 is negative 3. Negative 3 squared is 9. The opposite of 9 is negative 9. Negative 9 plus 5 is positive 4. So I'm going to label this height 4, even though, I mean, it's kind of close to 4. Guess what? It's 4 again, because I say so. Whoops. Please always label your curves by its function name. F of x represents y values. I don't want you to call this curve f of x. You can refer to the function y equals f of x if you like. That's specifying that outputs on this y-axis are given by outputs of that function. You could also label the entire equation. But the faster way is to call this relationship f and to call this relationship g. So there's my curves sketched and labeled. Got it? Try it out.